Hello, how are you? How are you doing, my professors, my colleagues, and my friends? It's me, Mourad Sultan Ezouidi, the pioneers in methods. Today we are going to give two examples uh, of solving 11-degree polynomial equation. So welcome everyone to this session. Welcome everyone to this special last. So welcome everyone to this special session. Today we are not just solving a polynomial, we are challenging mathematical history itself. According to Abel theorem, general solution for 5-degree and higher polynomials are impossible using radical. The door was closed. Mathematicians stopped searching. But Professor Mourad Sultan Ezouidi says otherwise. Through the power of Ezouidi theorem, a new path is revealed, one that leads us beyond the classical limits into the exact algebraic solution of even the 11-degree polynomial equation. Today I will demonstrate this, not with approximations, not with guesswork, but with precise and exact roots. Abel said no, but Ezouidi says yes, it's solvable. And I will prove it's right now, okay? So let's start. So our title of our session today is solving 11-degree polynomial equation and redefining the limit of algebra. Today we are going to see that we redefine the limits of algebra. So this session presents by the Professor Mourad Sultan Ezouidi. Today, as I told, we have made, or today we make history. Sorry, today we make history. I will show you how two equations that expose the failure of all classical methods, included including Abel's theorem, and reveal their exact roots using my own method called Ezouidi's theorem or Mourad Sultan Ezouidi theorem. Our objective here in our session today, we demonstrate the failure of classical algebraic method in solving certain high-degree polynomial equations, and to introduce Ezouidi method or Ezouidi theorem as a breaking through that delivers exact symbolic solution and symbolic solution where tradition fails. So let's start. I will share the lecture with you so that you can see the lecture. I have two examples, okay, of 11-degree from the equation, and we are going to solve this one. So now you can see, let's say, my screen, okay. Let's start. So here you can see that to demonstrate the failure of classical algebraic method in solving certain high-degree polynomial equation, okay, wait till it will open, and then we continue. Okay, we told that to demonstrate the failure of classical algebraic method in solving certain high-degree polynomial equation, and to introduce Ezouidi theorem as a breakthrough that delivers exact sample solution where tradition fails. So first example, we have this first example, 11-degree polynomial equation. P of x equal x raised to the power 11 minus x raised to the power 10 plus 55 divided by 11 square x raised to the power 9 minus 165 divided by 11 cubed times x raised to the power 8 plus 330 x raised to the power 7 all divided by 11 raised to the power 4 minus 461 divided by x raised to the power 5 times x raised to the power 6 plus 456 divided by 11 raised to the power 6 times x raised to the power 5 minus 315 divided by x raised to the power 7 x raised to the power 4 plus 145 divided by 11 raised to the power 11 times x squared minus 40 divided by 11 raised to the power 9 times x raised to the power 2 plus 4 divided by 11 raised to the power 10 times x plus 1 over 1 over okay 1 over 11 raised to the power 11. This one is going to be equal to 0. This is our polynomial to the power 11. And this polynomial to the power 11 can be written in its standard form. You can see the coefficient of L minus 1 is 1, L0 is 1, L1 is 55 divided by 11 square, L2 is 165 divided by 11 cubed, up to L10 is equal to minus because different signs, so that's why it is minus 1 over 11 raised to the power 11. So solving using Ezouidi theorem. This is Ezouidi theorem, or the structure that has been developed by Mr. Mourad Sultan Ezouidi. So Professor Mourad Sultan Ezouidi explains that this structure will give you the coefficient of a new 11-degree polynomial equation that corresponds to this original 11-degree polynomial equation. So when putting k equals 0 or k equal 1 or k equal 2 or k equal 3 or k equal 4 or k equal 5 or k equal 6 or k equal 7 or k equal 8 or k equal 9 or k equal 11, 10 and 11, so we will find that the value, or then we derive that S0 is 0, S1 is 0, S2 is 0, S3 equal to 0, S4 is equal to minus 1 different to 0, S5 is equal to 0, S6 is equal to 0, S7 is equal to 0, S8 is equal to 0, but S9 of all the Q is equal to minus 1, and S10 of all the Q equals 0. You see, S10 of all the Q equals 0 means you will get the first root, okay, that is singular fact, which is equal to 1, which is equal to L0 of ODQ divided by 11, because the last term here, S10 is equal to 0, meaning the L alpha, the first root is 1 divided by 11. Okay, so we can write, as we found, let's say, the value of this S subscript k minus 1 from the Ezouidi theorem, you can write your new polynomial equation as that x to the power 11 minus 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 s0 of O dq raised to the power r times, let's say, x raised to the power 10 plus s1 of O dq x raised to the power 9 minus s2 of O the q x raised to the power 8 plus s3 of O q x raised to the power 7 minus s4 of O q x raised to the power 6 plus s3 s5 of O q x raised to the power 5 minus s6 of O the okay, I will make this clear for you so that you can see it. Okay, it's better. Like that. Okay, make 14. I will make this 14 so that it will be clear for you. Okay, 14. So, okay, we told that you can write a polynomial as that. As let's say here, my professors and my learners and my students and my colleagues, that all the s subscript k minus 1 are equal to 0 except s4 and S9, which are equal to negative 1. So we can write your polynomial as that. P of x equal x raised to the power 11 minus S4 of order x raised to the power 6. Because this is S4, okay? X raised to the power 6 plus S9 of 42 times x. You can see that x is a common factor, or x is a no. So we can write this as x raised to the power 10 minus S4 of order Rx raised to the power 5 plus S1, S9 of 42 equals 0. Now I will use my the value of S1 Q dash, which is equal to negative This one can be written as negative 2 chosen S4 S4 q raised to the power 2 plus 4 S9 of OD2. So n here is 2. When putting x raised to the power 5 equal y or equal capital X, means you are going to work with second degree from the equation. So it will be negative S4 of 42 squared plus 4 times S9 of 42. Meaning that the value of S1 of 42 equal negative, then you are going to substitute S4 with minus 1, to the minus 1 squared, plus 4 times minus 1. So this one is going to be minus 1 minus 4 equal minus 5. Therefore, S1 of 42 is minus 5. So minus S1 of 42 equal 5. Why it is minus 1? Because here you can obtain a second degree equation, a new second degree equation that is relative to the this one when putting x capital X equals small x to the power 5. Okay, and you will get that x squared plus s1 of 42 dash equals 0, means x squared equal minus s1 of 42 dash. That's why here the negative sign is that. Okay, now what is needed now, x raised to the power 5 equal what? Equal x equal s4 of order r plus negative root of negative s1 of 42 dash, which is this one. So make substitution as x5 equal that, means that x subscript k from 0 to 4 is equal to s4 of ODQ plus negative root of negative s1 of ODQ dash divided by 2 all raised to the power 1 over 5 times exponential 2ik pi over 5. Okay, so these, in fact, is the value of xk. And here xk, where k from 0 to 4, it's written as s4 is minus 1. You see s4? This is s4. Okay? This is s4 is minus 1. So, because this is plus S4. S4 is negative. Negative 1 plus negative root of 5 divided by 2 all raised to the power 1 divided by 5 exponential 2 ik 5 divided by 5. Now put a positive sign and the other root are negative sign. So x from 0 to 4 is minus 1 plus, because this is plus negative. Okay. Root of 5 divided by 2 raised to the power 1 over 5 exponential 2 ik pi divided by 5. Or x subscript from 0 to 4 is equal to minus 1. And you see this negative sign? It's written as negative root of 5 divided by 2, all raised to the power 1 over 5 exponential 2k, 2k, 2k I pi divided by 5. Now, my learners, what's you can see that this is the first fifth x let's say x exact roots of these new 11 degree polynomial equations, which are equal to minus 1 plus root 5 divided by 2 raised to the power 1 fifth exponential ik pi divided by 5. Okay, and these are the exact x's. Okay, also we have here x subscript from xk x subscript k from 0 to 4 is minus 1 minus root of 5 divided by 2 all raised to the power 1 over 5 exponential to ak pi over 5. You see the negative sign, we can write it as positive sign. Change this as that will be 1 plus root of 5 divided by 2 all raised to the power 5 exponential 2k plus 1 I pi divided by 5, because minus 1 you can write as exponential I pi. Therefore, we found now the 11th x roots of my new 11 degree from the equation. Now we are going to write the roots, the exact roots of the original 11 degree from the equation. So alpha subscript k from 0 to 4 is L042, which is 1, plus x subscript k, these x's, the x roots, all divided by 11. So L0 is 1. Okay, L0 is going to be 1. Okay, okay. This is the first we want to do it. Yes, okay. Stop, stop, stop. No need. Okay. So here So now I'm going to change this value here. I will take all of this. This is the first. No. Okay, I take this. Okay. Copy. I'll put it here. I'll make 1 plus. No. That. Come back. So this is the first example that we found that precede the exact roots. Okay, and here we redefine the limits of algebra. Okay, and solving n degree polynomial equation and beyond, more than n plus 1, more than n plus 2. Okay, everything of course is really theorem. Okay, this is the first example. Then we are going to see insuitable uh, another example. Okay, that tells you that the method of Abel or Isaac Newton or other method are wrong. Okay, so I will take this one. Okay, I will make as -1. No problem, I'll put it again. Control G. Okay, so this is the first fifth root, and the second will be like that. Okay. Okay. Come here. So plus. We told the other five roots are written as L042 plus S subscript from 0 to 4, not 9, 0 to 4. Erase this. It's clear again. Okay. Okay. This one is the okay. Let's see. Microsoft comes like hacker. Hacker would say. Allah Ali. So 4. Okay. Then it will be this is plus. Okay. This is we call it plus. Again, then come here and add 2k plus 1. 2k plus 1 because it is negative. Okay, make between parentheses, one is here, erase the I, okay, plus 1 times, okay, times I pi, times I pi, all divide by 5, okay, all divide by n, because this is the formula. And these are exactly no guesswork or approximation method. This is exact precise work. Okay, and this equation satisfies, and this root satisfies your equation. Means when you put p of the polynomial, p of the root, you will find that is a no whatsoever the value of k here. And you see before that we told that x equals 0. So x subscript 11 is going to be equal to 0. That's why we make L0 for 2 plus 0 is 1 divided by 11 is the single root. Now let's see the second example, the classical failure. Okay, the second example, it's called the classical failure. Means the, we tell you the Abel theorem is wrong. Okay, we tell you that Isaac Newton is wrong. Approximation method is wrong because it will give you a decimal number like root, okay, as a decimal number, and is not, and this decimal number or this root can satisfy the equation. Okay, so we will get rid of all the classical method. Okay, let's see this example. You can see this one. This is our 10 to the power 11. Okay, this is it's called what? Unsuitable for classical method. This 10 to the power 11 is unsuitable, not good for classical method. Okay, means it will bother these, it will bother all these methods. Okay, so second example, the classical failure. So P of x equals x raised to the power 11 minus 33 x raised to the power 10 plus 495 x raised to the power 9 minus 4,455 x cubed x raised to the power 8 plus 26,730 x raised to the power 7 minus 1,012 1,266 x raised to the power 6 plus 336,798 x raised to the power 5 minus 721,710 x raised to the power 4 plus 1,082,565 x cubed minus exponential 5I pi divided by 101 x squared plus between parentheses negative 5,849 and 800 and we call the negative parentheses negative 5,845,851 plus 6 times exponential 5I pi divided by 101 times x plus 9,565,938 minus 9 times exponential 5I pi, okay, over 101, which is equal to n. So this polynomial to the power 11, it's called is let's say it's unsuitable, not suitable for classical method. Okay, so it's unsuitable for classical method. No classical formula, no reduction, no radical expression works. Repeat again. Comes here, Mr. Malik, if possible. So we told no classical formula, no reduction, no radical expression works, meaning that all the previous method or classical method that you already know is insufficient to solve or is unable to solve this unsuitable method. Okay, so but Zweidi theorem delivers. Okay, deliver that as 0 of order 0 is 0, as 1 of order 0 is of order as 1 of order r is 0, as 2 of order r is 0, as 3 of order r is 0, as 4 of order r is 0, as 4 as 5 of order r is 0. So as 6 of order r is 0, as 7 of order r is 0, as 9, except as 8 is equal to negative 1,082,565 plus exponential 5I pi divided by 101 all times by 11 raised to the power 9. And S10 is going to be equal to 0. We can see that S10 is going to be equal to 0. S9 is going to be equal to 0. Meaning the last two coefficients of our new 11 degree from equation are 0. Means you will get a double root. You will get, for example, alpha equal 33 divided by 11, which is 3. It's called a double root, or it's called a root with multiplicity of 3. Okay? So, why? Because S10, the last coefficient of the new 11 degree from equation, is 0. Also, S9 that comes after S8. S8 is different to 0. So, we derive this and we'll obtain, my kids, come here. Okay. And we'll obtain what exactly? Okay. And we'll obtain that P of x equal x raised to the power 11 minus a 0th order q x raised to the power 10. Yes, plus s1 of all q x raised to the power 9 minus s2 of the rx raised to the power 8 plus s3 x raised to the power 7 minus s4 x raised to the power 6 plus s5 x raised to the power 5 minus s6 of the r x raised to the power 4 plus s7 the cube of x minus s8 the square of x plus s1 of the r x minus s10 of the r. I will replace now the value of s subscript k minus 1. I will obtain immediately x raised to the power 11 minus S8 according to. Why? Because S8 is different to 0. And this is S8. You see minus S8. Okay, S8 is negative here. So minus S8 x squared. Then I'm going to put x squared equals 0. Or x 9 raised to the power 9 plus. Why plus? Because this is minus and that minus. Minus multiplied by itself is going to be positive sign. 1,082,565 plus exponential 5 I pi divided by 101. We close the parentheses, multiply by 11 raised to the power 9 equals 0. I'm going to transfer this value on the right hand side. It will transpose with a negative sign, and this negative sign I will write as exponential I pi. Okay, and this one p of x has to be equal as that. We told that I'm going to put x square equal 0, means x subscript 10 and 11 are equal to 0, means x equal double root here. That's why the root of our 11, original 11 degree from equation has double root. So x9 equal minus this. Okay, so this minus I will write as exponential I pi. So this can be written as minus 1 million between parentheses 1,082,565 plus exponential 5 I pi divided by 101, all multiplied by 11 raised to the power 9 times exponential 2k I pi. Okay, and the minus 1 I will write as a I pi. Multiply by this will give you 2k plus 1 I pi. So x subscript 10 and 11 are equal to now, and x subscript k belongs to 0 to 9 is going to be equal 1,082,565 plus exponential 5 I pi divided by 101 times 11 raised to the power 9, all raised to the power 1 over 9. Exponential 2k plus 1 times I pi divided by 9. So here you can see that, therefore, x equals 0, it's a double root, or x subscript k from 0 to 9 is 11. You see this 11 raised to the power 9? All raised to the power 1 over 9 is 11. I will put outside in front of the brackets. It will be 11 times 1,082,565 plus exponential 5 I pi over 101. Raised to the power 1 over 9 times exponential 2k plus 1 I pi divided by 9. So this one, these are called the x roots of the new 11 degree from the equation. Okay? And to find the roots of your original 11 degree from equation, write alpha subscript k from 0 to 8. Okay? Of course, this is 8. Yes, it's 8 here. This is 8 with Mourad. Okay. And this one is going to be 8 also. If it is 9, so you have 12. The highest power is 12. Okay, this is 8. So we told that we continue. We told that now to find the roots, we can write alpha subscript k ranges from 0 to 8 is a 0.42 plus x subscript from x subscript k from 0 to 8 divided by 11 because the highest power is 11. So 0 is 33 plus 11 times exponential 2k plus 1 I pi divided by 9 times 1,082,565 plus exponential 5 I pi divided by 101. Okay, all divided by 11. This one. So you see 33 divided by 11 is a 3. Then 11 divided by 11 is 1. 1 multiplied by this. Therefore, the ninth root of my ordinary level polynomial equation can be written and expressed as exact roots because these roots satisfy your equation. When you put p of alpha has to be equal to 0 whatsoever the value of k. So it will be the roots are equal 3 plus 1,082,565 plus exponential 5 I pi divided 101 all multiplied by of course raised to the power 1 over 9 times exponential 2k plus 1 I pi divided by 9. These are the ninth root, ninth exact roots. Okay, and alpha subscript k from k equal 10 and 11 are equal to L0 42, L0 is 33, xk are going to be equal to 0 like that. So it will be 33 plus 0, 33 divided by 11 is 3. 3 is a root of order of multiplicity. Or we can say that uh, is, is a root is a root of multiplicity. Okay, so these are my kids, the two examples. These are the two examples. Okay, the uh, the as the yes, these are the two examples of for mastering the solution of the 11-degree equation, where all the classical methods are failed or faded. Okay, so here final words, my professors. If classical algebra fails to find these roots that I found in front of you and in this live session, I explain it using my theorem and using my method. And I told you that this method is very powerful because it opens the door to get inside, let's say, to get, to get, let's say, yes, to get and send the field of algebra and to get redefine the limits of algebra and yet they are here explicit and exact, means my roots are explicit and exact. Then it's not the equation that is insolvable that I gave you two examples of 11-degree prime equation. Okay, that's not insolvable, but the method that is absolute. Okay, absolute. Abel said no, formula exists. Today I say yeah, here it is. Okay, we say again, if classical algebra fails to find these roots that I found before and that are beyond in front of your eyes, and yet they are here explicit and exact, then it's not the equation that is insolvable, but the method that is absent. Abel said no formula exists. Today I say here it is. Conclusion, my professors, we can say that we can say that I will now to make conclusion. Ezouidi theorem is not just a breakthrough; it redefines what is possible in algebra, where classical theory fails. This method reveals truth through exact sample solution. The how to say it? I will say it in other words: the frontier once closed by Abel and Galois, has now been opened. So this presented by Professor Mourad Sultan Ezouidi, inventor of Ezouidi theorem, contributing authors and research symbolic algebra. And I'm going to give you some books that I published. Authors are Mastering the Resolution of 10th, 9th, 8th, and 7th degree polynomial equation, solving 6th and 5th degree polynomial equation using Ezouidi theorem, exact solution of 4th degree polynomial equation beyond the classical method. Also, I published a book that is written in Dutch edition, and also another book is written in French edition. It's pronounced as that. Méthode de résolution de polynomial degré n. Nouveau théorème et méthode de résolution de polynomial degré n. L'SBN, I also got my SBN 978 620 3423. Okay, we continue. I will show you, let's say, my books. I will share first this one for you so that you can see. These are my books. Okay. Méthode de résolution du polynomial degré n. I have more than 10 books, in fact. All of these are my books. I published in edition of edition. Okay, just a moment. Yes, all of these are my books. Putting to the power n books and whatsoever. Okay, these are my books, my professors and my learners. You can be benefit from it. You can buy it if you want. This is how to solve things to the power n. Okay, and many theorem, in fact, in this book, maybe 20, 30, 20, 20 theorem with their proof. Okay, of course, focusing on solving things to the power n. Okay, these are the books. So, by the way, now I'm going to explain the two examples that I gave here. Okay, these the examples that I gave. You see. Now let's go step by step. Okay, let's wait. Let's stop here. Stop at Microsoft really comes like that. Doesn't work. Stop the session. So this is our prime to the power 11. I will write it. I will read it again and prepare yourself to solve to solve uh, to solve 11 degree prime equation. Now I will give you the steps. Okay. So let's see if it's possible to, yes. So this is the end, or this is like mastering the solution of an different equation using my theorem. Okay, and here in this book we define the limits of algebra, and we demonstrate that Abel's theorem and the second Newton method and approximation method are now unavailable. Okay, uh, in precise. Okay, because my method is very precise and will give you exact roots. Okay, but the classical method will never give you uh, exact roots as I explained it. Okay, let's continue. Here, the polynomial to the power 11 is that, okay, this one. So, p of x, now 5 down, I will erase this h. Okay, so this is p of x equal x into the power 11 minus x into the power 10 plus 55 times x into the power 9 divided by 11 square minus 165 x raised to the power 8 divided by the cube of 11 plus 330 x into the power 7 divided by 11 to the power 4 minus 161 x into the power 6 divided by 11 raised to the power 5 plus 456 x into the power 5 divided by 11 raised to the power 6. Then to the power, yes, 11 to the power 6 times x raised to the power 5 minus 315 11 raised to the power 7 times x raised to the power 4 plus 145 x cubed divided by 11 raised to the power 8 minus 40 x raised to the power 2 divided by 11 raised to the power 9 plus 4 divided by 11 raised to the power 10 times x plus 1 over 11 raised to the power 11. Okay. So now to solve this polynomial equation, we should use Ezouidi method or Ezouidi theorem and get rid of all the classical method like Abel theorem, the second Newton, approximation method, matrix, whatsoever. Okay, because they will never give you exactly. Even Abel theorem told that to solve a polynomial its degree is more than or equal to 5 is impossible. But we, let's say, explain it that we can solve 11 degree, 12 degree, 13 degree using the theorem of Mourad Sultan Ezouidi. So, Abel's close the door, Mourad open it. Okay? So, now you can see this one. Let's focus on this one to the power 11 to find out the roots of this polynomial. We should determine the values of SR for the Q relative respectively to LR for the Q, where R belongs to the set of numbers from -1 to 10. Now, these are the coefficients of my 11 degree polynomial equation, and I'm going to use Mourad Sultan theorem, which is S subscript k minus 1 over 2 equals the sum from 0 to k, combination n minus r choose k minus r, multiply by minus L0 42 raised to the power k minus r times Lk minus 1 over 4. So when putting k equals 0, you will find that 1 equals 0, equal 1. When putting, let's say, k equal 1 in the decimal formula of multiple really, you will find that s0 is equal to 0. Let's now dive into the structure and put k equal to. We find that s1 is equal to 0 when making our substitution. Okay, you would make substitution and we'll find the value of S1, which is equal to negative combination 1 to 1 times combination n to 2 times 0 to 2 squared plus n squared times n1 to 2, which is equal to half to minus 1 to 1, which is 1 times minus 2 to minus 11 to 2, which is 55, multiplied by 1, let's say by 1 squared plus 11 squared times 55 divided by 11 squared will be negative 55 plus 55, which is equal to 0. Yes, it will be negative 55 plus 55 is going to be equal to 0. So here we dive into also the structure and put in k equal to 3, and we see that S2 is equal to 0. Now at least we found S1, S2. Now we move to find S3. Just dive into the structure and put k equal to 4, and we obtain the S3 is equal to 0. Just make substitution. Okay, you see this is 11 cubed divided by 11 cubed to be cancelled out. Just put the variable coefficient that is on the numerators, meaning that negative 3 times 11 4. 11 4 is 330. Okay, so plus 9 2, 9 2 is 36. Is 36 multiplied by 55. Minus 8 multiplied by 106. Yeah, 65 plus 330. Okay, this is the word. When you are, let's say, a slept person, you are blind, you have a bird in different, in let's say different spaces and in color spaces. 1 second you touch this, so the color, you have direct ear, you have direct moon, and so on. And you, okay, so we continue from that. I will see if it works. Okay, I'm still with you, my professors, my colleagues, and my learners. Just answering what happened to the stream. Just a moment. Outcome is here. Go to Facebook. Okay. What is live? Yes, this one live. Okay. Yes, alas, I found it. So we continue. I will share the screen with you so that you understand, okay, and we will practice this theorem of multiple Ezouidi that uh, that will help you to find the roots of this 11 degree polynomial equation. So we call that, let's dive into the structure and put k equal 8, we find the value of 7, as 7 is equal to that, make your own substitution, and you'll find that 7 here is equal to this. Now we continue the figure 7, just we replace L0 with its value, S1 with its value, L1 with its value, and L2 uh, up to and 7, yes, and we find that the value of this is going to be equal to an L. Now let's dive into the structure and go put K equal 9 in Mourad Sultan Ezouidi theorem, and we'll find that, and we'll find that hmm, okay, Microsoft, bad Microsoft, not good for your sessions. So, so we continue. Okay. So, word Microsoft. Okay. So we call that. Now to find the S8, we found that the value of S8 here is going to be equal to 0. Just apply this formula and make your own substitution, and you'll find that S8 equals 0. Now let's dive into the structure again and put K equal 10. Or in other words, use multiple Ezouidi figure. You can see that this is S9, okay, that is written in terms of the coefficient of the original aggregate equation and the binding coefficient, okay, and the highest power m, okay, which is 11. So this one is 9. So just make your own calculation. You'll find that the value of S9 is going to be equal to minus 1. Put here S4 is minus 1, S9 is minus 1. Okay, so and the other coefficients of this new aggregate equation are all equal to 0. We continue, means that now we are going to dive again into the structure and we'll find that the structure, I mean, use Murat Ezouidi figure and put k equal 11, okay? And you'll find that this one is equal to an L, okay? So this is, it's called an insuitable example for classical method, okay? Because no classical method, even double theorem, can solve this kind of question. Because he thought that there is no general formula. But we, the Professor Mourad Sultan Ezouidi, explained and let's say tells you that here we are. And if you close the door, we open it. Okay? And we redefine, let's say, the limits of algebra. Okay? So let's continue, my professors. So this one now we call the S10 is going to be equal to 0. We can see that S10 is going to be equal to 0, means that we get, let's say, the first single root, which is equal to 0. Means alpha equal 1 plus 0 divided by 11. The first root is 1 over 11. Okay, because the last term is going to be equal to 0. Therefore, I told here, All the s subscript k minus 1 are equal to 0 except s4 equal minus 1 or s9 equal minus 1. Now this polynomial to the power 11 can be written as xn to the power 11 minus s0 for the r x10 up to minus s10 of the r are equal to 0. So you are going to cancel all the S10 and S7 and S6, S5, S3, S2, S1, and S0. So your polynomial to the power 11 can be written as xn to the power 11 minus s4 of order xn to the power 6 plus s9 of order times x equals 0. Means that x equals 0 or x is to the power 10 minus s4 of order x is to the power 5 plus s9 of order I equals 0. Now you can use this formula of Mourad Sultan Ezouidi when n equals 2. You will find that the negative sign is the opposite of the delta that you use to work. Okay? And the conception of, let's say, tell and discriminant formula while being a student is not like that. Okay, the discipline formula that you think, in fact, can be written as x squared plus s1 of 42 equals 0. Okay, means s1 of 42 is the second coefficient of the new second degree form equation corresponds to the original second degree form equation. This is how you should think. Okay, so, and those who thought that we obtain expressive, let's say, or reduced or um, expression or equation from, for example, n plus 1 to get n degree in the equation, not expressive. Okay, there's a point. There is structure. There is a way to structure. Okay, so we told that x raised to the power 5 equal, because we are going to use this one, s1 of 42 equal negative s4 of order q squared plus 4 times s9, means s1 of 42 dash equal negative minus 1 squared plus 4 times minus 1 gives minus 1 minus 4 equal minus 5, minus s1 of order q dash equal 5. So s x raised to the power 5 equal s4, because this is s4, plus negative the root of negative s1 of order q dash, which is s1 of order q dash is the second coefficient of the new second degree from the equation. When putting small capital X equals small x raised to the power 5. So here imply that x subscript sorry, k belongs to the set of numbers from 0 to 4 is s4 of order q plus the negative root of negative s1 of order q dash divided by 2 all raised to the power 1/5 times exponential 2k plus 1 2k I pi divided by 5. Now I will replace s4 with minus 1 and s1 root of s1 q dash by 5 as that. So then this is simplification. You take you so the first fifth exact roots, the first the first fifth exact x roots of these new 11 degree polynomial equation are written as that: minus 1 plus root of 5 divided by 2 raised to the power 1/5 exponential 2k if I divide by 5. Or the second, first, fifth exact x roots of these polynomial to the power 10, 11 are given as that: minus 1 minus root of 5 divided by 2 raised to the power 1 over 5 exponential to ik 5 divided by 5 equal, I will put minus 1 as exponential I pi, then it will be written as 2k plus 1 I pi divided by 5. So these are the x roots, the exact x roots of the new 11 degree polynomial equation. And x equals 0, so is the 11th, 11th x root. Now to find now, let's say the first fifth exact roots of the original 11 degree from the equation, just make the substitution as 0 for 2 plus x subscript k from 0 to 8 to 9, yes, divide by 11. So it will be here, my learn, okay, I should change this, okay, so it will be, we call the, okay, I will take this one, it's better, okay, only this, only this, okay, yes, so now make plus, okay, plus, and here make minus. Okay. 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 Control C. Now these are the exact roots. Then I will make here plus. I will cancel the one also. I'll make 1 plus root of 5. Minus 1 we put here in the explanation. So these are the exact roots, okay, with a precision. Okay, we precise, let's say, the solution here. The solution are exact and real, and P of alpha equals 0 whatsoever. Okay. And alpha subscript K11 or alpha 11 is a 0.42, which is 1 plus x subscript 11, which is 0 here. You see this one x equals 0. I will replace with 0, so it will be 1 over 11 is going to be okay. Now, use your own calculator and do your best. This is the pioneers multiple really was with you. Thank you for listening. Inshallah, today, maybe after 2 hours, I'm going to explain another example, okay, where I will show you this example, okay. This example I will, you see this one? These are the coefficients of this one. I'm going to change this. Meaning this one is 55 over 11. The last coefficient is 12. Okay. And 9 is going to be 17. Okay, this example I will do. I will write here, not finish it, not finish it, not explain it. Okay, it's better not explain it, not explain it. I will explain it in next live session. Thank you for listening. This is the pioneers. Mourad Sultan Ezouidi was with you. Professor Mourad Sultan Ezouidi, Professor Mourad Sultan Ezouidi explain it for you, professors and learners, students, colleagues, and those who think good, those who believe in science, those who believe in research, that we really open the door and we close, let's say, or we put away, we put Abel theorem uh, in the past, okay? Because Abel closed the door. Professor Mourad Sultan really opened it again and redefined the limits of algebra and got rid of he gets rid of the Newton method because they will give wrong answers and they can't, let's say, find exact roots like the method of Mourad Sultan Ezouidi. And it is a honor. It's a pleasure for me to share the knowledge with you and to let you make advancement and explore the field of mathematics. Thank you and goodbye. This is my fingers. Goodbye. Okay.